I was the lackey for the smart people running BSides Tampa. It's now an absolutely huge conference. You want to get really involved in InfoSec, you want to network and whatnot, go volunteer for BSides San Antonio. But Richard runs the whole thing. He's awesome. But don't hassle Richard today or any of the other organizers because they're going nuts. You really want to impress them. Mark on your calendars about 30 days from now to go reach out to the organizers of BSides San Antonio and say, I would like to volunteer to help you guys. And it's amazing how much more impressed they'll be that you reached out to them when they're not going in 500 different directions. So yeah, do go check all that stuff out in the local area. So story time. Let's say you're running you're working for a local retailer, a regional retailer. Let's say this retailer sells coffee. And let's say this retailer, not just coffee, this retailer, it does drive-through coffee, and maybe it's called Danish Sisters. That sounds good, right? So anyway, you're working for this company, and this company's just really doing it right. You're doing all of the cool AppSec stuff, all of the cool application stuff. You're full all sorts of DevOpsy and whatnot. You're so cool. You've got Kubernetes clusters in all of your stores that are doing who knows what. And the people, the developers that have developed this stuff, they've mostly done a good job by handling the PII, the personally identifiable information with their applications. But everybody messes up now and then. Stuff happens. And if you think this scenario I'm describing is insane, there's a well-known chicken place across the country that's been running Kubernetes clusters on really crappy desktop hardware. It's like HPs or desktop, some crap like that. And they're running them in the back of the store. That's what they're operating their stuff on in these fast food joints. So this isn't such a crazy scenario I'm painting here. So anyway, you're working here for Danish Sisters Coffee, and your CEO is suddenly freaking out because he read in the Wall Street Journal this morning about how some burglars ran into a retailer that had some stuff that in their retail store, and some PII leaked. And your CEO is like, all right, what are we doing to protect ourselves from this? And this whole Kubernetes thing was rolled out pretty quick. While they're mostly being pretty good about not holding on to PII and whatnot, there might be some leakage stuff ending up on disks and whatnot. The disks are not encrypted. And your CEO is like, we can't have this. We need encryption at rest with all of our stores. And you're thinking to yourself, all right, what are we going to do? Have our managers enter encryption passwords at boot? But we're doing Kubernetes clusters, so we're not running Windows. What are we going to do? So, you're like, CEO, I'll tell you what, I'll get back to you. And that's what you do. So what if I told you that bad people try to steal stuff?
I'm shocked.
What would happen if disks were stolen from your data center, or your cloud infrastructure, or your edge computing systems at Danish Sisters? Data theft is expensive. It's not good. And data at rest encryption, data at rest encryption is pretty good stuff. It'll protect you from common thieves that look something like this guy. But data at rest encryption will not protect you from people who actually have real skills. It won't protect you either from ransomware, certainly won't protect you from elite hackers, not at all. And Linux root disk encryption. You got a chicken and the egg problem. So your system is booting up, and if you screw this up wrong, you're going to end up DOSing yourself. That's bad. If you manually enter a password at boot, like I was mentioning earlier, asking the manager to do that, that's pretty ugly. You could have extra servers, but now you've got a really juicy target. That's not the best solution. You could do some sort of vault kind of thing. But we're going to talk about something that in some ways is a little better. Maybe you could do TPM. I mean, this is supported on Linux these days, but it's ugly and it might make you suicidal. So, you know, all is not roses with the TPM, as I was saying. It's tamper resistant hardly means tamper proof. So here's a gentleman that I've heard in the Austin area. I'm not going to mention his name. I don't want to get him in trouble, and he probably don't want me talking about him. But he's actually been doing some stuff in some amateur research in like the back bedroom in his house, you know, his back room, where he's taking chips and he's shaving off layers of the chips and then pointing lasers at various bits of the chips and flicking bits on chips. And he's doing this. You know, it's not easy to set it all up. You got to line it all up and do a bunch of trial and error the way he's doing. And this is not the latest chip technology. This is, you know, chips from a decade ago. But he's able to do this at home. So if he can do this stuff at home, what do you think people can do with, you know, actual real lab equipment? You know, you think TPM is all that and it's all wonderful and all that. Yeah, I mean, with the right equipment, you can flick bits on stuff. And once generally, once you have physical access to stuff, you know, that's the end of it. Lasers, you know, there are other technologies that can do these sorts of things. But yes, you can flip bits on your, what do you call it? Lasers are real and they do stuff. Some more practical considerations. Here's a gentleman named Stack Smasher. He's a security researcher. And this guy, you know, when researching this talk, I found this video. I was just blown away. So I'm going to show you a video here in a moment, but I want to describe it first. This gentleman, and by the way, feel free to take photos of anything you see here, and also feel free to shout out any questions, anything that doesn't make sense to you. You know, if I'm going to come up with it later on in the talk, I'll let you know. But so this guy here, feel free, I'm going to have a slide at the end that has lots of this stuff with tiny URL links, and you can decide whether or not to trust them or not. It's up to you. So this guy is a security researcher, and this is not the latest iteration of the TPM. This is the previous iteration of laptops where the TPM, the Trusted Privacy Module, was actually a separate chip. But this gentleman put together a Raspberry Pico, a little device thing, and he is actually going to stick this. He did some custom programming, a whole bunch of custom work, and he's actually going to stick this thing over the legs of the TPM chip as Windows is booting up with BitLocker, and he's going to lift the decryption key for Windows, and then, you know, after that you can shut the drive and get full access to that encrypted thing that was encrypted with this super awesome trusted privacy module thing. This all happens very quickly, so watch closely with this video here. He unscrews the thing, the laptop, plugs it in, and then boom, you put that thing on the legs of the chip, and there's the decryption key. All that's needed after that is to shuck the drive, stick it in a Linux system or something like that, and you've got decrypted access of your BitLocker drive on older hardware. Obviously, this technique won't work where you have a chip that's you know, not a discrete chip that you can do this with, but you know, I was mentioning the laser things before. TPM is not some sort of, you know, end-all be-all. And once you have physical access to a device, you're kind of screwed. So what exactly is this whole TPM module thing? I mean, it's a computer. Is this a good idea? So I've got a computer in my computer. I mean, yeah. So, what if we didn't have to deal with any of this nonsense? What if instead we could do this thing called network-based disk decryption? You know, what if instead of TPM or this other stuff, there was another way to do it? So this tool that I mentioned at the beginning, Tang and Clevis, this is an open source set of technologies for Linux. And it's based on a theory that was developed by these two genius engineers at Red Hat. And it's, their names are McCallum and Rayla. I think I'm mostly pronouncing that correctly. And they've created this whole cryptographic thing. It's kind of weird in that when this whole cryptographic thing occurs during the initial handshake thing of it, you actually end up throwing away one of the private keys that's used in this, because it's only used initially when you're initially establishing trust and then never used again. And the decryption works at boot without escrow. It's based on Diffie-Hellman. So who here knows what Diffie-Hellman is? Handful of folks? All right. We're going to wander into a little bit of cryptographic nonsense here, but we won't get too deep. So Diffie-Hellman is the stuff that, every time you go on, your web browser goes on an internet, connects to an HTTPS site, and you're doing hypertext transport over TLS. Diffie-Hellman is being used in order to create a shared secret across the internet over a insecure connection where you don't have anything being shared between the two pieces. In short, both sides have a public-private key. So the public key is being shared over the internet. The private key is something that you know only to yourself. So you go past the public key to the other side. The web server also passes the public key to you. Some math is done, and then you do some additional math with your private key. And at the end of the whole thing, you create this large shared secret that only you and the remote server know. And no one else that observed this communication over the wire is the wise to as to what this shared secret is. It is very cool stuff, and it's worth looking into in more depth if this is something that really tickles your fancy. So the McCallum-Raylan setup, as I was mentioning, it's kind of like that, but a little different. So, in our example here, I'm going to show you a demo later. I mean, if the demo gods behave. So we've actually got here is I've actually got two what are supposed to be servers. Now this is supposed to represent a big iron server, or maybe it's just a desktop in the back of Danish sisters. But this is your actual server thing. And that's running a piece of software called Clevis. And then you've got another little lightweight thing that could be running on something lightweight. And it's running something called Tang. And if you look here, you got your big iron server. And the Tang server, the very lightweight thing, sends a public key to the client. The client generates a new public-private key pair. Some crazy math is done on the client, so this would be your server, your big iron server. The client then discards this private key because it's never needed again. Then, so this initial step is where trust is established. This is roughly similar to if you ever use SSH and you initially connect to a new server, you're asked, do you want to trust this? This is roughly similar to that, what's going on here. Then the next step would be when your big iron server is booting up later on, it generates a new public-private key pair. It does some math with this new public and private key pair. The Tang server, the little lightweight thing, does a little more math with the thing that the server sent up. And some more math is done on your big iron server. And at the end of all of this, the decryption key that's needed to decrypt the root file system, among other things, or any other file systems as well, on your big iron server, that is recreated so This server key didn't actually exist anywhere. It's not in escrow, it's not anywhere else. It was recreated from the initial trust step that was set up initially. And it's magic, this stuff. If there are any real math nerds that love discrete math, here is the discrete math explanation of what's going on here. This was grabbed off of the Red Hat presentation you see at the bottom. If anyone from Red Hat is here, don't sue me. Yeah, this is a cool presentation. It's worth checking out. And so, you know, there is actual real math behind this and real cryptographic awesomeness. This is, what's going on here is so close to Diffie-Hellman that folks, cryptographers have looked over this in depth, and plenty of cryptographers have signed off on this as so flipping close to Diffie-Hellman, it's secure. I mean, that doesn't mean that implementations out there couldn't have issues or that sort of thing, but this is probably okay. So, Tang server, I was mentioning that before. We've got our demo rig that we're going to look at in the future. The Tang server is nothing more than a lightweight HTTP server. Yes, you're reading that right. It's not using secure HTTP, HTTPS, because it doesn't matter, because the only thing that's being handed is already encrypted. And also, if you know anything about Linux servers, or if you kind of think this one through, early on in the Linux boot process, there's a very minimal Linux system that's set up initially, and it is very minimal. It's amazing that you can actually get this whole Clevis thing shoved in there. You don't want to have to also be doing HTTPS. There's no need to. So that's part of the reason, it's just keeping it simple. The Tang server is only using HTTP so that Clevis doesn't need to do HTTPS. You can run this on something really, really lightweight. You should be able to run it on something as lightweight as a Raspberry Pi Zero for hundreds of servers. This really is using very little. It doesn't matter, but I mean, it just is using very little in the way of CPU cycles to pull all of this stuff up. And the secure thing that's being passed over this lightweight HTTP server is a JSON object signed encryption file. We're going to look at that in a bit during part of our demo later on. So Michaelim and Raylo developed this thing. Clevis is the bit that's running on your big iron server, you know, or maybe it's just a desktop in the back of a store. But, you know, the thing you're actually trying to protect. It negotiates with that really lightweight Tang server. It uses a LUX slot to store its metadata. Who here is familiar with LUX on Linux? Okay, handful of Linux nerds here, awesome. LUX stands for the Linux Unified Key Setup System. I think I got the algorithm right. So you can still decrypt things manually, even when you're using this whole Tang and Clevis thing. So normally the way LUX would work, like on your desktop or something, is it boots up and asks you for a passphrase. When you're implementing this thing, you still have the option of using a passphrase. You just also have the option of having this automated thing that doesn't require any kind of user input. So a word on LUX, yeah, Linux Unified Key Setup. It has one master key. That is the thing that actually does the encryption. That's the encryption key for the Linux volume that you're using LUX to protect. Then LUX also has a bunch of slots, 8 user key slots specifically. So a LUX system would look, a LUX setup for a Linux volume would look something like this. You've got slot 1. I mean, this is what it would normally look like if you're running on your desktop or whatever. You've got slot 1 contains a passphrase. So normally when you boot up, you just enter your passphrase, and that's enough to recover the master key that will then decrypt the Linux volume. And you've got another slots 2 through 8 in there, so you've got quite a few options there. If you're using this whole Tang and Clevis thing you're talking about, so on our big iron server, our LUX volume for root would look something like this. You'd still have the passphrase at number 1, probably. that you used when you installed things up. And then slot 2 would be this awesome data that this whole Tang and Clevis thing are using. And that's what the system, it would, you know, look to see if there's any of this JWE data in any of these slots. If it is, it's going to try that. Pretty cool stuff. So ways to protect your Tang server. You remember, this could be running on a Raspberry Pi. You could be throwing it on the other end of a VPN. Now you need network connectivity for your systems to boot up, but that's one option. You could hide the thing. I mean, if it's a Raspberry Pi, it maybe could be in the ceiling. I mean, there's nothing wrong with a little bit of security through obscurity, right? Again, you know, it depends on what your threat model is and what you're trying to protect against. Your average burglar probably isn't going to go all the way through all the ceilings and that sort of thing. So that might be an option, at least your average unsophisticated burglar. For added security for all of this, your Tang server, you should probably periodically rotate your Tang keys, which means establish new ones. You also need to hold on to any keys that were used in order to establish trust initially with any Clevis systems that are out there. So you don't necessarily want to delete your old ones. You want to create a procedure for this. Cryptography is not trivial. You know, it requires work to actually do it right. And yeah, who wants to see a demo, huh? Yeah! All right, so we're actually going to do a proper demo. I do have a backup option, but who wants that nonsense? So what I'm going to do, this right here is the HDMI switch thing that I've got my laptop plugged into. I'm going to unplug that, so you're not going to see anything on the laptop. And I am going to find the HDMI cable in this rat's nest and plug it in over here. And then, sorry, the screen is a little bit funky. All right, it did this before. I'm glad we tested this early. All right, kids, don't try this at home, but we're going to unplug the system and plug it back in again. So this is our big iron server that we've got plugged in here. And oh, there we go. Voilé, as they say in France. So this right here is our big iron server. And we've got it booting up right now. That's Grub. So I've got a USB keyboard plugged into it up here. I've got a network cable plugged between it and our Tang server. But in this case, both of these particular Raspberry Pis are Raspberry Pi 4, which is ridiculously overkill, especially for the Tang server. But, you know, I like to travel light, and Raspberry Pi 4s have USB-C. It makes life easier. That's why we're doing that. But again, like I said, there's no reason this couldn't be running something really light, where Raspberry Pi 3 would still be overkill. But we're just using a Raspberry Pi 4 just to make life easier. So again, we've got an Ethernet cable plugged between the two. This particular thing, functioning as a Tang server, only has power and Ethernet on the bottom. This has a lot more going on over here on our simulation of our big iron server. We've got Ethernet, we've got our USB keyboard plugged in over here, we've got power. Then also we've got mini HDMI, that's how you're able to look at all of this awesome here. And then I also have a USB stick, memory stick plugged in here. I'm doing that to make life easy. Trying to make trying to install Clevis on the Raspberry Pi is much easier if you're doing it on, say, a USB device like this. In order to make this work, I'm actually booting off of this USB device. In order to make that work, you have to do all sorts of shenanigans with UEFI, with Raspberry Pi. You wouldn't have to do any of this stuff if, say, you were doing this on a x86 PC. It would be much easier. It was hard to make it work on this Raspberry Pi stuff. But hey, it works on ARM64. It's pretty cool. Yeah, anyway, we've got that USB. This right here is actually running off of that USB stick. And so on this system here, I'm going to log in, and I can't really see it over here. Let's see. Okay, so I logged in there. Let me come over here. Let's see how this works. All right, so I'm logged in there, and if we look here, I've got a handful of files here, and in particular, I'm interested in a file called Tangent. So I'm gonna cap that file. Can you guys see this back there?
Yes, sir.
All right. So if you look at this particular script, it's very simple. What it's doing is it's running the Clevis command, and it's passing an argument encrypt, and then it's using tang as the pin. You could use other pins. For instance, you could use, say, TPM or other things. We're going to cover that in a little more detail in a bit. Then after that, it has a URL that's in some JSON, and it's put in there with an IP address. Why? Because that makes the demo much easier. Of course, you could actually do DNS and actually do this properly if you're actually doing this in production. You probably wouldn't want to do that. So I've got that, and then that will encrypt something. So for starters here, let's encrypt something. So I need some audience participation. I need a short word or phrase that we should encrypt.
Pterodactyl.
Something I can spell.
Please.
Please. Okay. How about yes, please?
Okay.
With an exclamation point. Okay, and I think I did a what do you call it, quote there? Did we do that right there? Yeah, that looks right. All right, so I'm going to pipe that into my Tangent command. And I'm going to redirect the output of that into a JWE file. plz.jwe. Okay, so I'm going to hit enter here. So this is my big iron server that I'm currently connected to, and it right now is asking me, hey, do I want to trust this remote Tang server that I'm connected to running on the other Raspberry Pi? And it's got a string there. Now you can already establish a trust if you're actually doing this in production, so it's not asking you this question. You probably should do that. But this is a demo, so we're just gonna say why. And now if we look, let's clear the screen. If I cat the PLZ file, we have this big ass string. Okay, so I have another command there called decrypting. That's much, much, much simpler. All it says is Clevis and decrypt. So I'm actually not even going to run that. So we're going to take the cat from this, I'm going to pipe it to Clevis, decrypt. And boom, there is our magic hidden phrase. Now, what just happened here, I mean, this is what's happening at boot. You can actually use it to store any kind of messages, and that's what we're demoing here. This phrase didn't exist anywhere. It was encrypted in a fashion where you need both components. You need both the big iron server and both the Tang server. If you only have one, you have nothing. The message is lost forever. You must have both. When you have both, and that magic McKellar-Raylan handshake can occur, and the system will boot up. So that's how that part works. Now, the cool part, or extra cool part. So we are going to reboot the system again, except this time I am going to disconnect the network cable. Here, let's disconnect the network cable on the Tang server. So now you only see one cable plugged in there, the power cable. And now I'm going to power cycle our simulated big iron server here, and it's going to boot up. And it's thinking about it. By the way, to make all of this Raspberry Pi stuff work, you have to actually flash your Raspberry Pi to make all of this UEFI nonsense work. It's a whole thing. I've got a link at the end if you're interested in doing this sort of stuff with Raspberry Pi 4. I couldn't believe how much work it was to make all of that work. So what's going on here is the system is booting up and there's a bunch of noise and it's saying, hey, and I'm trying to contact the Tang server. Now, I could, at this point, type in the passphrase, and the system would continue to boot up and decrypt as normally. We don't want that. Let's just say we had a slight network hiccup at this point, and the network hiccup is resolved, and we're going to simulate that by reconnecting the network wire. And maybe it reconnected. And like magic, the system continues to boot, because before that, it was encrypted, and the handshake with the Tang server occurred. The root file system and boot file system was decrypted. The system finishes booting. There we go. Fantastic. Any questions? Question, yes.
So I'm looking over the demo, but how do you integrate that with the actual boot part for the OS?
How do you integrate that with the...
How do you integrate the like Tang, this part, to the boot part of the OS?
With the what part of the OS?
The booting part.
Oh, the booting part of the OS. Yeah, I'm not really going to cover that in depth in this talk, but the short answer is you install Clevis locally. You're going to need to set up a Tang server somewhere. And there are detailed instructions on the Clevis website about how to establish the initial trust and how to install it into your bootloader. And you want more details, feel free to talk to me afterward. Any other questions with the demo part before we move back to the rest of the presentation? All right. So we're going to disconnect that and reconnect this. Boom. How are we doing for time?
Pretty good.
All right, cool.
You got till 4:15.
Awesome. Okay. And here was my backup slide in case the demo didn't work. So what the solution protects you from, like I was saying before, protects you from common thieves. But what about really sophisticated thieves with skills? So, you know, duh. Ultimately, they have you in your data if somebody really, really has skills. So if somebody, you know, with actual skills is the one breaking into your Danish sister store, you're in trouble. If someone with real skills, say, pays a hobo to and gives them really, really good instructions on how to do everything, you're probably also hosed. I mean, it's just reality. I mean, once you have physical access to stuff, it gets ugly really, really quick. What we're talking about here makes life better in general, but it's hardly a panacea. So you can make things a little bit better. Maybe if your threat model would warrant it, you could do more defense in depth strategies, even with this solution. For instance, if your Tang server goes down, none of this works. If your Tang server is over a VPN, none of this works if the VPN goes down. But Tang also supports, Clevis and Tang, Clevis supports using Shamir secret sharing. So theoretically, you could have 3 Tang servers, you could have 5 Tang servers, and you could require a certain quorum of servers in order to actually have all of this handshake work. So you could make it so that, say you've got 3 Tang servers, you could make it so that when the system is booting up, you need at least 2 Tang servers in order to reconstitute the key. So if one of the 3 goes down, you're still fine. If you want 5, then you could require 3 servers and so on and so forth. You could also require both a Tang server and TPM2 on your hardware. So if you want to be extra paranoid, I mean, we said TPM2 is not some sort of, you know, panacea, can be worked around, but now you just made things much more complicated if you're requiring both TPM2 and a Tang server that's on the other end of a network. Now it's going to be much more difficult to decrypt that particular hard drive. You know, assuming that they didn't grab the key out of RAM when it was still running. I mean, there's always ways around it. So you could also require both TPM2 and or a quorum of Tang servers with the Shamir secrets sharing. You know, with great power comes great responsibility. You need to figure out what your threat model is and choose the right amount of complexity that actually you can justify in terms of the cost. None of this is free. Earlier I was talking a lot of trash about TPM. You know, I mean, TPM 1.2 was a complete dumpster fire. It was horrible. TPM 2 is not nearly as bad. I mean, it still is a computer inside a computer, but it's not nearly as bad as what we were dealing with before. So, you know, I mean, BitLocker, UEFI, Secure Boot, like I was mentioning, all of this stuff, it's a small computer running inside of your system. It has an API, that's a whole lot of attack surface. TPMs are also kind of slow. Not that that really matters. I mean, your system doesn't boot up that often. TPM, you know, what can it do? It can, beyond just this sort of booting up thing, you can actually use TPM to do things like store open SSL keys. This might be an interesting application if you've got, you know, a bunch of web servers. You know, you can validate that tampering hasn't occurred, at least theoretically. I mean, it has some functionality to measure certain things during booting, and you know, maybe that'll, you know, save you and make it more difficult to tamper with stuff. You can conditionally decrypt volumes at boot, much more, whatever. More complexity means more potential for DOSing yourself. Don't shoot yourselves in the foot. How to avoid catastrophes? You know, how to avoid CrowdStrike-like catastrophes where you DOS yourself. You know, what happened with CrowdStrike? They had some really cool software and they pushed out an update and they DOS'd yourself. As you're rolling this stuff out, you need to be really careful so you don't get fired. That's just reality. Network-based decryption means it makes yourself dependent on the network. It makes your systems dependent on the network. It requires your network to have some sort of internet connectivity, probably. Some questions you might want to ask yourself. How valuable is the data that you're trying to protect? You know, nerds like to get all excited about cool technologies, but you know, I mean, the grown-up nerds ask this sort of question. How valuable is this data actually? You know, what would the cost actually be if that data is stolen that I've got in my store? What would the cost be if the data is distributed? Given my threat model, how do I hide my keys? And in this case, my keys are my Tang server. Also theoretically the other server, but that's where your data is stored. It's your Tang server. So the total cost of disk decryption, what is the total cost of rolling it out? It's not free. It requires a lot of man hours to actually test this sort of thing, then put together a plan to roll it out. What is the ongoing cost of maintaining this solution? It's not free. Your time is worth money. The other people involved with maintaining this, their time is worth money. So ultimately, we need to secure with a purpose. I mean, the short answer is the cost to implement and maintain our fix had better be less than the cost of, you know, a security breach or the bad security thing happening times what we guess the probability of that thing happening is. There is no point in spending way more money than, you know, for something that's very improbable. You know, for something that's very probable but also very cheap, we also don't want to spend a lot of money for that. So, I mean, we need to justify what we're actually doing. In the case of this particular thing here, in the example I've got earlier with Danish sisters, how good are we doing with our ability to keep PII off of the spinning disks, if we've got spinning disks or SSDs or what have you? How good are we doing that? And what would the risk be if some of that actually leaked out there? These are questions that they're ultimately business decisions. Takeaways. Tang and Clevis are open source, as we mentioned. You need both the Tang server that's now on the floor and the Clevis, the big iron server, in order to decrypt what's on the disk. If you only have one, you've got nothing. You can add extra decryption requirements to it, to Clevis, like we mentioned. You could add TPM2. You could also require a quorum of Tang servers, or you could do both. Make sure your encryption solution makes business sense. So, your CEO at Danish Sisters comes back to you and says, so what are you doing? You're saying, we, sir, have a solution, or ma'am, have a solution where we are rolling out on-disk encryption on all of our systems, and we're going to require network connectivity when the systems boot up. It's not ideal, but all we need is just a little bit of network connectivity, not a lot. We're going to look into, making our network more robust, so when the systems boot up, that is there. And at this point in time, if somebody steals our servers, they're encrypted. And this isn't a panacea. That doesn't mean that there isn't some weird angle where somebody who has really good talent, if you've got really people with lots and lots of money and lots of skill that want those systems, they might break in and do something really clever, but we're going to make it much more difficult. We're going to raise that barrier of entry, so it's really difficult for them to get our data, and your CEO says, hey, good job. You have greatly reduced our risk, and you've just made it much more difficult for people to mess with us. Good job, well done. Thank you, folks. Feel free to take photos of this. Questions?